Okay, if this is the case, let's now use this to understand how we express the components of a vector to begin with in these two different bases, right? What's the relation between the components of a vector in one basis and another? So, in particular, let's consider, right? Let's consider a vector, say U, okay? And when I say U belongs to R3, we're just reminding ourselves of the fact that this is a vector in 3 dimensions. Okay? We have 2 bases now. So let's write U in terms of both bases. So U can be written as Ui EI in one basis, or as U bar I E bar I in the second basis. The question we are trying to ask is, what is the relation between the U bar and the U? Okay, what is the relation that goes between those two? So the way we are going to do this is to essentially invoke the sort of expression that we derived for the relation between the E bar and the E bar I and the EI. All right? Okay. So the way we'll do this is the following. We will say consider the following. Let's suppose we want to look at the j component of U in the barred basis. Okay, that's U bar j. Okay, the way we would write that, because we know these properties of bases, is to write it as U, the vector, dotted with E bar j. But then we know that we can write E bar j. We can now express E bar j in the original basis, right? The unbarred basis, right? We did that several times on the previous slide, and we will do that again. In particular, let me write that as Q kj ek. Okay? And recall, what I'm doing here is to write E bar j, okay, a vector, in terms of the unbarred basis. All right, and the particular arrangement of indices on the Q just comes from the way we define the components of a tensor, and we did this in a previous segment. Okay, and this is really the relation that we're using all through here. Okay, all right. Now the QKJs are just scalar components, so that the dot product's linearity allows us to go through and write this expression out on the right-hand side as Q kj U dotted with ek. Okay, but now we know that U dotted with ek is simply the UK component. All right, where that component is expressed with respect to the original basis. Okay, and so this gives us our relation. U bar j is QKJ UK. All right. Now, we can write this using linear algebra notation. Okay. Using the notation from linear algebra, we can ask ourselves, well, if we now arrange the components of U in the barred basis as a vector, right? In particular, if we wrote this as, if we said that we wanted to write U bar 1, U bar 2, U bar 3, okay? We wanted to arrange them in a vector, and we wanted to ask ourselves, what is the matrix that relates this arrangement of components with the arrangement of components in the unbarred basis? Okay? What that expression here tells us is that the matrix that goes in here are simply the components of Q transpose. Okay? Why transpose and not Q itself? Think about it. Why Q transpose and not Q itself? The answer comes from the previous line, right? Look at how the indices are contracting. Okay? That form of contraction is what we always write as Q transpose. Okay? So this is the relation that we have between them. This is the relation between the components of U in the original unbarred basis and the components of U in the barred basis, both treated as vectors using linear algebra notation. Recall, however, does the vector itself change when we change these bases? Okay? No, the vector does not change itself. Okay? So that's worth putting down. Okay, so we note the vector U is invariant. Okay? What changes are its components, right, in the two bases do change. Okay? How do they change? Exactly the way we wrote it before, right? Okay, so the way they change is U bar j equals Q kj uj. Okay? Let's now quickly also look at how this works out for tensors. Okay? So using this idea, let's look at change of tensor components. All right? The same idea. Consider a tensor A which belongs to this general group of linear operations on 3 dimensions, right? And that's how we wrote it out, GL3. Okay? Now, just as for the vector, the tensor doesn't change, right? The tensor is invariant. We are just going to write out its components in terms of the two bases. Okay? So, we will get the following. We can write Aij as Ei dotted with Aej, or we can write its components in the barred basis as A bar ij equals E bar I dotted with A E bar j. Okay? And now, as before, we are going to ask the question, how do we relate A bar ij to A ij? The approach we're going to follow is just what we did for tensors, except the fact that we have two basis vectors involved in this product to give us the components. Okay? So, we're going to write A bar ij equals, we're going to rewrite that expression from there, E bar I dotted with A Ej bar, okay? And then we're going to use exactly the relations we used in doing this operation for vectors. So, on the right-hand side, we write it out as, first of all, writing out E bar I in terms of the original basis as Q Ki Ek dotted with A, and E bar j is now going to be written as Q L j E E L. Okay, so now that we've got that bit sorted out, let's just crank through with the properties of the dot product and tensor multiplication of vectors, both of which are linear operations. Okay, so that is Q Ki Q Lj, okay, and we have here Ek dotted with A, E, L. All right? We know very well what that is. Right? It allows us to write it as Q, K, I, Q, L, J, and EK dot A, E, L we know is just A, K, L. Right? That component. All right? And so we see, when we carry this product through, we see that A bar ij is related to the A components, right, in this fashion. Let me just bring this also here so that we have that final relation. Okay? A bar ij equals Q, K, I, Q, L, J, A, K, L. Okay? And when we write this out in its final form, the way we can do that is A bar ij equals Q. Let's just remember what components we had. Ki on the first one. So we have Q, Ki, we have A, KL, and Q, LJ. Now, in terms of just the components of A in the two different bases, we observe that we can write this out as A bar 1, 1, and so on, A bar 1, 3, all the way down to A bar 3, 3. If we arrange these components in a matrix, what we see that this can be written as some matrix multiplying the A11 through A13 through A33 components times some other matrix. And those two matrices simply turn out to be, right, the Q transpose components, and here the Q components. Okay? So that then is the relation between the tensor components in the original basis and in the transformed basis. All right? To finish up this segment on the effect of change in basis, there's just one more relation I want to put down for us here, which is the following. Okay? Let's recall this sort of expression, right? E bar I is equal to Q E I. All right? Now, we know, and we've often used this expression today, we can write the right-hand side as Q K I E K. All right? Finally, if we take this expression and dot it throughout by one of the unit vectors belonging to the original basis, right? Let's suppose we do this. Ej dotted with E bar I. Okay? We apply it there, and what we get is Q Ki Ej dotted with Ek, which is Q Ki delta Jk. But this, after all, is just Q Ji. Okay? That's an important result. Okay? What it tells us is that the components of the Q matrix, if you like, are obtained by forming this sort of dot product. Okay? So what this says also is that Q Ji components are the direction cosines of the Ej basis vectors, right, relative to the E bar I basis. All right. So that's very useful, because if we know the two different bases that we want to use, right, if we know that we have the original basis, let's say the unbarred basis, and we have the barred basis, we know what the transformation is between them. Okay, so we'll stop here for this segment.